So we are going to wait another 5 minutes. So if you have time, you can maybe go to this URL. So this contains all this material I'm going to talk. So actually, I only have 2.5 hours, so I cannot cover all of them. Actually, most of the tutorials, it's a new book we are writing. So this, if you click any link, you can go here. This is the HTML of the Jupyter notebooks. So actually, the source code is on. Let me see. Run these tutorials. You mean this web page? Oh, this Gluon. Let me show you here.
Excuse me. Can you speak a little more to the mic?
Oh, yeah, sorry. So the URL, it is. It's gluon.mxnet.io. If you click any link on this URL, you can go to this web page. So this is a bunch of notebooks. Actually, this is runnable. If I click, I don't think I click the page source, but so let me get that. Yeah, sure. So if you're gonna, all this notebook is runnable. So if you want to run this ones, you can click at the bottom, the page button. There's run. Let me zoom a little bit. So at the bottom, there's a page called Run These Tutorials, which tells you can how to install this. You only need to have Python environment. For example, you need to install Jupyter notebook and also MXNet. So then it should be fine. It should work both on Mac, Windows, and Linux. So when we install these ones, all this notebook is hosted on this repo. You can click the link. So it actually contains a lot of stuff. So this is a new book. Actually, we didn't finish all of them, but it covers the basic usage of MXNet. Also covers a bunch of, basically, we're going to show how to write deep learning or machine learning from scratch, not just using the high-level interface. We also show you how to write all these algorithms from scratch, basically using the tensor or like a NumPy-like interface, so you can write all of them by yourself. Also, we also show how to use the high-level interface. So most of the tutorials, we have two versions. So first, the from scratch version. Assume that you don't need to use any deep learning framework, and also using the high-level interface. So this is actually a large book. We didn't finish all of them yet, so we just started 3 weeks ago. Hopefully, we can get a more complete version by end of next month. So actually, we will cover all this deep learning, the state-of-the-art algorithms in deep learning. So the most interesting thing here, most of the notebook you can click is runnable. So if you follow the instructions, you can run this notebook locally. So okay, I think it's 9 o'clock, so let's start it. I'm going to So for today's tutorial, I'm going to first spend 20 minutes to give a brief introduction what we are doing now, and then the rest of time I'm going to go through all these notebooks and also give more high-level ideas what is implemented. So basically, so all these deep learning frameworks has been moving very fastly. If you use the TensorFlow, if you use the Keras, they are moving, the front-end interface is moving. Especially, the new trend is we want actually to make researchers using this deep learning framework more easily. Previously, we may be more focused on how to deploy deep learning products into there, but now we finally realize that, okay, research and the product can be together. You don't need to sacrifice research or sacrifice for products. So we're going to show how a uniform solution to give both research and product. So here we see that there's a bunch of deep learning frameworks. So they're necessary. Nobody can write deep learning from scratch because if you have hundreds of layers, it's pretty hard to write all the things from a normal Python or normal C++ front end. Deep learning framework provide a lot of features. The most important one is firstly auto-differentiation, which means you only need to write the forward path. You don't need to specify how to calculate gradients. Secondly, because these deep learning frameworks the deep learning algorithms are pretty expensive. So most of the people using GPUs, most people use accelerated frameworks to library to make it faster. So most of the framework provide these two important features. So there's a lot of them. Just the older one is Cyano. Then TensorFlow improved Cyano. So TensorFlow mostly take a lot of Cyano users. Caffe is another very old framework, which is a default one for computer vision for a while, for a long time. Then there's Caffe 2 version. CNTK is kind of similar to Caffe, but it's kind of more Microsoft style. And Keras, you can think Keras is more like a simplified TensorFlow. There's another framework line is Trainer. Trainer is developed in Japan, which is it's purely imperative. And then PyTorch follow Trainer's interface. MXNet sits kind of between, which is called MXNet. We're trying to mix this programming flavor from the bottom part and the top part. So we can roughly classify these frameworks into two categories. The first is the imperative. The second is the symbolic. So imperative is the normal way we write Python programs. So we write and execute and get a result. Symbolic is more like you first define the networks, and then I can compile and feed with data. So I'm going to show you how the difference between these two guys in detail in the next slides. So in the next few slides, I'm going to explain the basic idea of each framework and what is the advantage, what is the disadvantages, and what is the new one we need to address. So Caffe is the default one for deep learning for a while, as mentioned before. So it has the only interface Caffe gives to users is a proto buffer. So if you used Caffe before, you can check the Caffe, the proto, so which defines all this layer interface. So which is clean. Everything here is on the proto buffer file. So if you write Caffe, if you train a Caffe model, you finally only get the text definition of the network and the binary format of the parameters. So this is the only thing you have. So if you want to deploy, Caffe uses C++ front end, you can train on the command line. So which means Caffe is pretty portable. You can compile Caffe, the C++ code into different frameworks, different platforms, and then you can deploy easily. But the problem here, if you read and write in proto buffer, it's not very convenient. So even that Caffe have a Python binding, it's kind of still not Python style. So if you see that this is a ResNet 101 layer is provided by Camin. So this actually have 4,000 lines of code. definitely it's not generated by hand, but if I give you a product buffer, if you unfortunately change something, you never know what's going on there. So TensorFlow is another developed by Google. It's another very popular framework. The advantage is that it's like TensorFlow have 300 engineers to develop this framework. It provides a rich set of operators. So currently, if you check the website, it tells you it has over 2,000 operators. So basically, it has anything you want. But the problem is that because you have so many operators, the code is not very easy. It's not very Python style. So if you check this code, this is to implement the underscore t equals beta 1 times a and plus something. This is a single line in the Atom optimizer. So this is TensorFlow implementation. So if you see that, oh, it's not. So you have state op dot assign and something like that. So get slot, something like that. So it's pretty not Python style. People use it because, well, once you get it there, you can easily to deploy. This is good for product. But somehow, to implement this single lines of algorithm, you need to write 4 lines of code. This is not straightforward. So the learning barrier for TensorFlow is actually very high. Keras, on the other hand, trying to simplify the interface. So here's the Keras how to define a two hidden layers, multi-layer perceptron. So you first call sequential, which is a container, allows you to push all these layers into a queue, and then you add a dense layer. It tells, okay, it tells that the dense layer output is 512, and the input shape is here. Then you can do dropout. You add another dense layer. You do dropout and add another dense layer. So once you finish the definition of the model, you can compile, and then you can run a training by model.fit. So it's pretty easy to use. I think a lot of data scientists are using Keras these days, especially when you go cargo competition. A lot of guys are using Keras. But the problem here is that the interface is very high level. So which means it's pretty difficult if you want to implement the new algorithms. So for example, if algorithm you have more like if you have for loops or if else conditions on the network, it's very hard to implement. So in this case, Keras is more like to use existing network is fine, but if you want to use Keras to do research, it's a little bit harder. So all these 3 frameworks I show you all follow the symbolic way, which means you first define the network, the whole network, and then you can compile, and then you can feed with data. The advantage here is that when you compile the program, you know the whole computations, which means the backend system know all the things you want, and you can do a lot of optimization here. So I'm going to show you on the later how optimization can be done for the symbolic interface. But the problem here is that, well, you cannot debugging. So if you model add, if I fit with the data, I want to get the output of the first dense layer is hard because kinds of you need to add print operator into the network and compile and fit again. So it's not like a normal way we write Python. So PyTorch and Chainer are trying to solve this problem. So it follows the purely imperative style. So this is how to implement a 2-layer, a single multi-layer perceptron with a single hidden layer. So you define a network. Then when initialization, you initialize 2 linear layers. So FC1, FC2, also you have a ReLU here. Then you define the forward function. The forward function tells you that, okay, given the output, given the input X, I can first apply the FC1 to get output, and then apply ReLU and apply the FC2. So I return out. So in which case, all this forward function is executed each time when we run the forward pass, which means if you want to print something, if you want to print out of the output of the first fully connected layer, FC1, you can actually print. So this is pretty convenient if you want to debugging something and track the things. So anything is clear here. So even that you're writing a little bit more lines of code, it's pretty straightforward to read. It's more like a Python style here. But the problem here is that, well, it's a little bit slow if you have a very complicated programs, because everything here is in Python. Each time you need to execute all these line by lines. It's good. It's not a problem if it's a small code. Each FC1 fully connected layer is huge. Then the overhead of launching the Python code is not so big. But if you have a lot of tiny operators, then the Python actually, the overhead dominates the whole thing. So, well, this makes researcher easier, but if you want to care about performance, if you want to, another thing that if you want to deploy, you need to have this Python code ready, which means when you deploy into product, you need to use Python. So another thing, MXNet, the original interface we trying to find is kind of, okay, most likely the most of computations is on the network itself. So in this case, we can let people to write symbolic program to define the network. So here I call, so I first give a batch-long layer, and then apply to the activation, this ReLU, and then connect to a convolution layer. This is a small part of to implement the ResNet. Secondly, we found that, okay, the algorithm itself usually requires very flexible way to implement things. If people want to print something, you usually print the optimization method, how to print the gradients, to print the weight. So in which case, we let people to write optimization method using the imperative way. So here, this is you're using basically very similar to NumPy to write tensor operations code. So that's why we call it MXNet. NetHome, so this is kind of 3 years ago. 3 years ago, all these network instructions, definitions, it's kind of simple. So it's more like a sequential ones. So people can have it, there's no problem there. But nowadays, we realize that the research community is so active. There's more and more very dynamic networks. For example, the TreeLSTM, which is kind of, you construct a network based on the sentences of the input. So given the sentences, you build a syntax tree and to construct the tree-like algorithms. So in which case, implement these things in the symbolic interface is not so convenient. So that is why we think, okay, so now we need kind of more flexible way how to provide to users. So this is how we started. It's mainly contributed by Eric, who's here. So the new interface is called Gluon. So Gluon trying to connect both imperative and symbolic on a unified way. People write everything in imperative, but then you can deploy as a symbolic later on if you care about the performance and if you want to deploy on the product. So this kind of solved the problem, the MXNet previous problem that, well, you can only define the network within the symbolic way. So now you can use the imperative. So this interface take a lot of things from, we learned a lot from the different frameworks. Firstly, the backend, we use MXNet, but the interface, we take a lot from the chaos layer definitions because we feel like the layer definition is pretty good, but the chaos, like model training is too high level. So research is harder to dive into the training loop. We also take a lot of ideas how to organize the training loops, how to write the program, to access the parameters to update the model from trainer and the PyTorch. So which is kind of called Gluon. Gluon is a physics term which is connect different particles. So next I'm going to show a very high-level idea, so what this looks like. So the first part we define, again, a simple hidden layer, multi-layer perceptrons. So this is very similar to chaos. You can have, you call sequential, which is container, and then you add a dense layer and another dense layer. And so all these two dense layers using the ReLU activation, and then finally you get output dense layer. So one important feature here, we don't need to specify the input size, which is very different to most, which is different to Keras, which is very different to PyTorch. So all this input shape we can inference later because MXNet have a symbolic engine behind that. So this we find it's very convenient because most of the time people actually cannot inference the input shape pretty well. It's like especially you have hundreds of layers. Then you define a loss function. This softmax, you first apply softmax, and then you give a label, you can do the cross entropy loss. Then the following block is a training loop. So given, I assume there's a get batch function, which returns the data and the label each time. Then within autograd.record, which means we need to record all this trace, so then we can compute the gradient later. So we first apply, given the data, we apply to the net. So this is called forward pass. It returns the output of the last fully connected layer, and then we apply to loss function. You get the label. So the good thing here, all these things are imperative, which means you can print anything at any time. I'm going to show you later for the notebooks tutorials. So later on, I can, because I record all this, how it's computed, I can call the backward function. So then I can compute gradients. Finally, we can do a train.step. Given the batch size, we can update the parameters. So this is how a training loop, network definition, and the training loop looks like. So all the things here are imperative. So basically, it's a Python code. Then if you really want to turn into a symbolic way, which is usually faster, and also you can get the language-independent definition. You just give the net called Hybridize. Hybridize turns the internal execution from imperative to symbolic. Basically, what do is, because in the first time I execute this forward pass, I know all this computation here, and then I change it into a purely computational graph. And then next time I call forward pass, I don't need to go back into the Python code. I just use the internal computation graph. So in this case, we reduce the Python overhead from Python to C++. Also, the computation graph can be dumped into a JSON file. So you can use this JSON file to deploy on the other framework, front-end languages MXNet provide. For example, you can do inference on R, on Scala, and on C++. So this is the basic idea of what Gluon provides. In summary, the framework, different frameworks have two styles. First, the symbolic, which runs faster, but it's kind of hard to use. The barrier is higher. You need to learn a lot of things. You need to turn how you think the program into a more symbolic way. Basically, this is how users learn SQL. The imperative is flexible, but usually slower. So what we're trying to do that we want to provide a unified solution, which means you can faster programming using the imperative way. You can enjoy everything imperative have. And then if not only you want to care about the performance, you want to deploy, you can simply convert into a symbolic way. So this is a basic idea how the Gluon provides. Next, I'm going to show notebooks, actually give you hands-on experience how to use the new interface. I'm going to mirror my screen. So is there any questions? Again, so because we don't have so many people, so we can, if you have any questions, we can answer the questions. Any questions? Yeah, sure.
Are there utilities then to convert formats, say, between Cafe?
Yes, so we do have tools which allows you. So basically, we provide two things. Firstly, we have tools to convert directly from the Caffe product buffer model to MXNet. Basically, convert the product buffer into a JSON format, the symbolic JSON format. You can load, you can train, and inference. The other thing is more interesting is like, because what we learned is like, most of the people actually write customized operators in Caffe. So especially some companies have hundreds of new operators writing in Caffe. So if you want to switch the framework, nobody can rewrite this operator again because some operators is writing maybe 2 years ago, or the guy have already left. Nobody know how to do that. So in this case, MXNet provide a plugin that you to call directly into Caffe operators. So each Caffe operators can be mapped into MXNet operators, and you can use it directly. Also, we can use the Caffe data iterators and call directly. So we're trying to, so the philosophy of MXNet is trying to group different, because this frameworks developed over different researchers across different universities. We're trying to make a flexible thing to how to group different components together. Yeah, sure.
The other option is if you want to convert, I mean, sometimes maybe you want to run code from MXNet together with other code that runs in another framework. So you would like to convert back to another, what do you call that place as TensorFlow or Kappa. Can you convert it back to something?
Okay, so questions, can we convert MXNet to other frameworks? Yes, so we're trying to maintain official, there's third party on the GitHub trying to convert MXNet into Caffe. So basically someone write a unified converter. So everybody convert to Caffe and then Caffe to different frameworks. So this kind of thing. So yes, we're trying to have that one directly convert into MXNet into different frameworks. So also this web page, we have a new section, which is kind of a cheat sheet how switch between TensorFlow and MXNet. Currently, so TensorFlow is a little bit harder. TensorFlow have a bunch of scan while loops. We are trying to find better solution, which is not probably get a TensorFlow XLA internal representation and map into our internal representation. For PyTorch is easy. PyTorch Keras is like 1 minute to convert into the Gluon interface because they're pretty similar. For Caffe, yes. For Keras, MXNet supporting Keras framework. Basically, we have an MXNet backend for Keras. You can have native Keras code runs on MXNet.
I mean, actually, compared to Kappa, not from Kappa. I mean, imagine I already have a lot of code in Kappa, and I want to develop this wonderful program in MXNet, but I still, for legacy reason, need to run it on Kappa, so I need to convert it back. Even though maybe future products use MXNet all over, but I have some legacy stuff. I still want to have it runnable.
Oh, yes. So basically, this plugin called Caffe plugin here lets you run directly on Caffe operators. So you map each operators or each list of operators into a single operator in MXNet.
I have MXNet code, and I want to convert it to Kappa code.
Okay. Well, then, got it. So runs MXNet within Caffe is harder. Caffe is not not maintained anymore. The only way we have is we can map our definition into Caffe JSON and map our model, binary model format into Caffe model format. Then, but it's harder to run the actually front-end MXNet within Caffe because Caffe is not imperative interface. Yeah, sure. So yes, so you mean how to visualize the network? Yes, actually we do have a plot which print every layers and also the shapes between the connection between each layers. So I don't want to, so for imperative it's hard to print, but the way that for the imperative code we convert into the symbolic code and do visualize the thing because the graph kind of need the whole computation graph. Okay, got it. So basically, the question that want to visualize all this internal result. You want to visualize all this layer input and output.
If you're familiar with something like so, like you have these digits from NVIDIA,
Uh-huh. Mm-hmm.
give you this kind of visualization. So I wonder if there is something similar for this.
So we're trying, so we have NVIDIA Fox here. We are trying to make MSNet into digits so that you can use digits, the visualization tools. So we are also supporting TensorBoard. The TensorBoard also provide interactive way how to visualize the network, visualize the input and output. So we are also supporting that. Okay, so let's move forward. So the next I'm going to show is a bunch of notebooks. So because I cannot cover all of them, I only show some basic stuff from the first part. I'm going to show how to use the basic Gluon interface and use it to implement the linear regression to simple convolution neural networks. And on the second part, I'm going to show more advanced topics, such as how to convert between imperative and symbolic, also how to run multi-GPUs, even multi-machines from scratch. So if you want to try, actually, there's instructions. But what you only need to do, if you have pip, everything should be fine. Then you can install Jupyter Notebook. This is the thing we're going to use to run these networks. To install MXNet, you can pip install MXNet. Usually I add the -- pre here because I want to use the lightly built MXNet, not the stable one. Because the new interface is just it's not coming to. We will add into the next stable release. So currently you can only use the lightly built MXNet. So this one we install the GPU version. Then if you have So this one only have the CPU only version. So if you have GPU installed, then you can install, for example, if you have CUDA 7.5, you can install MXNet-CU 7.5. If you have CUDA 8.0, then you can install the according version. So next I'm going to show you. So. So basically, you can pip install. I already actually, let me show you. Let me uninstall MXNet first. So you can pip install pre MXNet. I'm going to install on my local folder, so I don't need to use sudo. So basically, it will be a download of 7 megabyte binary format, and then that's all. So basically, install the version. It's just today. So we build every morning of the day. So then I can firstly have a quick validation. You can run Python. You can import MXNet. Well, the first time it take a while. Then I can print the version at do you have. Okay. So also I can show you which MXNet are you using. So usually if you have multiple MXNet installed, you need to double check which kinds of MXNet version you have. So then have MXNet installed. Next, I'm going to clone this notebooks repo, which is git clone this repo. I run this one. So let me go here. So git clone this repo. then I go directly into this repo, and I use Jupyter Notebook, runs Jupyter Notebook. Then it tells you, okay, this URL you can open. Then that's all. So you can click any one, for example, any notebooks. So you can run on the Jupyter Notebook now, for example. Yes, so this is how to set up on Mac, on Linux and Windows. So next, I'm going to, following this tutorials, I'm going to use the EC2 instance because currently my Mac doesn't have a GPU. So I do have some code which runs on GPUs. So I'm going to, you can follow the similar step on the remote Ubuntu instance on AWS. Then once you installed, very similar approach. When you installed, I can SSH to that instance, and which can open the notebook on the remote machine and run locally. So basically what I'm going to do here, I SSH to my instance, which is I create an alias called the dev. So the only thing here, I want to map the remote port. So basically, I'm going to open the Jupyter Notebook on a particular port, and then map into my local machine, so that I can use my local browser to access that port. I'm going to show you -L. Then I map the remote port into my local host port. So this is well, the network here is not so. Let me close my previous one. So next I'm going to start screen, and I open the Jupyter Notebook. In particularly, I want to use the port. I want to use this particular port, so I can map here. So then it returns another URL. I can click. I can open on my browser. So now, all this notebook runs on the remote machines. So it's very similar to run on local machines. You can access anything here, so it's pretty convenient. So now I'm going to use the remote notebook to run a bunch of tutorials. The first one, so all these tutorials I can run is listed on the website. Actually, but it's have a lot more here. You can, if you're interested, you can go through all these notebooks. It doesn't assume any deep learning background or even any machine backgrounds. So it's built everything from scratch. But if you know machine learning deep learning before, you can faster jump all these sections. So the first one I'm going to show is the dimensional array interface. So if you use NumPy before, it's very similar to NumPy. So I'm going to show you here. The basic thing I want to import MXNet or NDArray as ND. So I set the random seed here, and let me do. So I can import, this is a setup. So then I can create empty arrays given a particular shape, 6 by 4. Then I can print the actual value you have. So then this is 6 by 4 arrays. So because it's empty, there's nothing there. So all this is uninitialized. But most likely you want to create a random matrix. So this is called a random.lomo, which is called a random matrix, which is 0 means one standard variance data, given the same shape, 6 by 4. So now you have a random matrix. So similar to NumPy, you can print the X shape, by using the shape. And also you can print the size, how many elements you have on this array. This is very similar to NumPy. So next I'm going to show some basic operators. So I create another normal matrix. I do element-wise plus. I can print the result. So this is another 6x4 arrays here. So you can also change to element-wise times or minus, that's fine, yeah. Basically, all these element-wise operators should be supported. And another one that maybe I can show that is exponential. Yeah, you can call ESP here. So this is basically operators. So next I can show you how to do in-place operators. So the previous one that each time I return a C, I create a new array here. But sometimes you want to in-place the result. So the in-place result, you can do bracket colon. Then, so you create the result here. It's all zeros. And then I tell that I don't want to override the I want to create another result. I just want the result to sit directly into the result here. So I can specify these operators. So basically get everything to the in-place. So here's the tricky one, a little bit tricky here. So plus equal, in default, do the in-place. So I create x, I let y point to the same x has, and then I create this one. So basically, y will be equal to x. But if you do this one, y equals y plus x, you actually create another new result and assign to y. So this is kind of Python style. For Python, each time you create a new objects and to assign to this one. So slicing is very similar to also NumPy. So I can slice from row 2 to end of to 4, but doesn't include 4, the rows, which is kind of the row 2, row 3 doesn't include row 4. So you can get the result here. You can also access a particular element. Because this is a 2D array, you can assign, okay, the row 3 and column 2 be equal to a 9, and then you can print the result here. You can print the third line of x here. So if I'm going to print the whole x, so basically this row 3, so row started from 0, and the column 2, column started from 0 as well. So I get this element here. So you can also access to give each axis a particular range. For example, here I'm going to get the row 2 and 3 and the column 1 and 2 here. So this is kind of a sub-array of this matrix. I can also assign this array, this region to a particular value. So this is kind of given to 5, and then I can give this region to 5. So this, if you familiar with NumPy, this is all similar. So because NumPy is so popular at Python, we have a function called sNumPy, which returns a result to NumPy. So then you can enjoy everything NumPy functionality you have, and then for example, I create all 1, 0 on the array, and then I convert it into NumPy. So B is I can print the type of B, which is a NumPy on the array object. So it's very useful. Sometimes, if we do have operators doesn't implement on MXNet, we can call directly to NumPy and do some using NumPy operators and convert back. Convert back is it's basically called NDArrays. You can convert the NumPy NDArrays back to MXNet. So also this is kind of, even that no matter what the MXNet NDArray state, you can either on CPU, on GPU, call as NumPy usually every time works to convert into NumPy here. So okay, so this is basically basic operators and converting to NumPy. The next thing is the additional feature MSNet support. Yeah, questions?
So why can't you just use NumPy the entire time and just don't even use the MXNet NDArray?
Okay, so that's a good question. So the question is that why not just use NDArrays, NumPy NDArrays? So I'm going to show you on the next few tutorials, which is additional feature we provide beyond NumPy. So that's why NumPy is not good enough. For example, auto differentiation, also GPU support, also lazy evaluation, so you can parallel all this computation together. So this is the first the additional feature we provide to NumPy. In default, when you create the array, so B is a NumPy array here. I can specify which context you're going to sit. In default, it's on the CPU. In normal, everything on CPU memory. But then you can also specify, if GPUs are available, I can specify GPUs. So the first time you initialize on GPU take a little bit of time, but I can print, I can print D. So D is no longer on CPU. So it tells you that this is an NDArray which sits on GPU 0. Similarly, if you have a CPU thing, you can copy to a particular device. A GPU 2, I can, for example, D is on GPU 0, I can copy to GPU 1. So then you will see that it's on GPU 1. Okay, this kind of thing. Another thing that you can give the as in context. So this kind of copy to every time copies. As in context, if the counter D is on CPU 0, then as in context returns directly to D. But if not, it copies. So basically, it's a tiny syntax sugar. Next thing I'm going to show, if you NumPy before, yes, we can do broadcasting, which is, so you create X is 4 by 4, but the Y is a vector with its length 4. So I can do, so basically this is Y, and then I can do X plus Y, which broadcasting the second element of Y into 4 by duplicate the Y's. So Y equals to 1. So this is Y, X, and let me print X as well. So this is X, this is Y, and then, this is capital X. So I can duplicate the Y along these arrays and then add into the previous one. Broadcasting, similarly, you can do a lot of more broadcasting stuff. So I'm going to quickly finish this very brief introduction to NDArray. Basically, NDArray provides a lot of NumPy NDArray features, operators, so that you use NumPy before, so you can very easy to get hands off the NDArray. Also, we show that one additional feature is the GPU support. You can specify the context to particular GPU you want. So the next tutorial I'm going to cover is another additional features, which is we added to NumPy. This is auto differentiation, which means you don't need to specify the gradient function. You can have using all these functionalities NDArray have and get the gradients. I'm going to show you here. So this is called the auto grad. So similarly, the additional one I do here, I import MSNet, the auto grad as a G. So this is the additional import for this tutorial. So similarly, I can create X. I can print X, what X it is. So X is 1, 2, 3, 4. It's a 2 by 2 array. So if next time I can do operators using X, if I want to get the gradients of X, additional one I need to do that I can attach gradient. So I'll test you that I create a gradients arrays, which is inside X, which stores gradients we can print later on. I can run this one. So basically, for each parameters you want to get a gradient letter, you need to run this parameter dot attach grade. So the second way you want to do auto differentiation is that you need to explicitly record this trace you deal to for the gradients, because we want to explicitly do that to avoid the user. If you don't do that, the system will record every step, which is kind of you have a system overhead, which means we let people to explicitly say that, okay, with this record, everything writing within this scope will be recorded. And later on, you can do gradients functions. So here, I do element times x with 2, get to y, and then z is equal to y times x. So basically, this is equal to 2 times x times x. So the gradients will be 2x. So I run it. So z is the output here. I run the z backward, which means calculate the gradients. Now that, because we know that with for x with for basically dz dx is equal to 2x. This is a gradient. So next I'm going to show you what is x gradient like. So I'm going to show you, I'm going to print x as well. Okay, my calculation is wrong. Oh, sorry, this is 2 times 2. Yes, it's 4. So basically, well, sometimes system is more smart. So this x, so the gradient with respect to z will be 4x. So that's, we get a gradient here. So this is auto differentiation. So any questions here? Okay, let's go a little bit forward. So another thing that doing the backward, I can specify the head gradients, which is if you run a neural network, you need to pass through the gradients. So for example, for this layer, you need to get the gradients for the chain rule from the header. So which means you can specify the head gradients applied to the here, and you can do, then you can still get an S grade. So this is one feature. Another feature, which is more like related to imperative. So as you see that here is pretty, little bit complicated one. For record, I use a while loops and if-else conditions here. So what I'm going to do here, I create X, which is a random matrix. And then B equals to X times 2. I do a while loop. The while loop is related to the long of B. So we don't know the length of the while loop yet. So we don't know how many iterations you can have because it really depends on the result of B. YA is a random variable. So then I stop until the long of B is less than, I stop until the long of B is larger than 1,000. And then next time I do if-else conditions. Also the if is really depends on the data you have. So I run, basically you can using NDArray operators with any Python logic control element here. So I can run this one. I can also specify the head gradients. I can do a backpropagate. I can print A. So basically I don't, well, actually, I don't know how to calculate this one, but you kind of assume this is correct. Well, you can, the thing that you can, okay, you can usually can print I equals 1, and then y do I plus 1, print I. If I is here, if it's B, I print 1, otherwise I can print 2. So basically I run 10 times, I times 2 by 10 times, which means the gradient will be 2 times 10, and then here I go, so this is the result. So the while loop, I iterate for 9 times, with the first one with 10 times. The second one, I goes to this branch, because it's print 2, so I times 100, so which is, the result will be 2 power 10, 2 to 10 times 100. 2 to 10 times 100. No. So then this one, we get head gradients, which is 0.1, which means the last, so let's go this one. So this is 1, so the second element, it will be, well, actually, my calculation is wrong again, so basically this is 11. Okay, so this is iterated by 10 times, and there's another one here, it's 2 to 11. So yes, so then the gradient will be here. So okay, any questions here? So basically with the imperative programming, you can write arbitrary complicated for the function, and then you can still get the gradients right. So this is very nice elegant feature for the element-wise programming. You don't need to write, for TensorFlow, you don't need to write actually TensorFlow scan operators, something like that. So here is more nature Python programs. So within this, basically within this NDArray and auto-gradation, so then we have the tools to implement most of, I think all of the deep learning frameworks, deep learning algorithms, because using auto-differentiation, you can easily get the gradients. You can update by hand, actually. So the next tutorials, I'm going to show you just to use this two interface. How to implement basic linear regression. So the second tutorial will be linear regression. So linear regression from scratch. So similarly, I import autograd and also NDArrays. And let me run it. So linear regression, I think everybody kind of know. Given input x, I times a vector w and the plus b, the bias, and get a prediction. So the loss function I'm going to have is L2 loss. So given the predict the y and the true y, I calculate the distance, square distance. So okay, I can implement these functions using from scratch. Particularly, I'm going to use a very naive 2. The weight is 2. The first true weight is 2, and minus 3.4, and plus a bias with a noise here. So basically here. So I first generate the data. I first create a random x, which is random normal distribution for the shape is 10K by 2. So 10K examples, 2 features. Then I create a y, which is the true y is 2 times the first column of x, minus the 3.4 times the second column of x, and plus the bias, and plus a normal a small noise here. So this is x and y. It's a small synthetic data set. So I can print what each example looks like. So it's here. Similarly, so this is a true label. Given the true label, and what we can do here. Also, we can visualize kind of the correlations between the first axis and the second axis. So given the input data set, what we should usually give, if we're going to run SGD here, what we're going to do is each time I'm going to read a small batch from the data. So you can write by hand, but currently MXNet have an iterator called MXNet.io, the NDArray iterator, which given the input x, given the input y, and I give a batch size equal to 4. Each time I'm going to return 4 elements, 4 examples, and 4 labels from it. I specify the shuffle equals to true, which is randomly shuffle the data set. So each time it's easy to implement stochastic gradient descent here. So there's a training data. So if you use Python before, each time it actually returns a iterable object, which means each time you call next, I can return a batch. So batch, we have both data and the label. So if batch, you have data, so you have data, and I print also batch dot label. So data is a list of input data because currently we have a single data. Sometimes we have multiple data. So here you get the 0 and you get label 0, which means there's 4 examples here for the data 0, and the label is like 4 length vector here.
This assumes all the data is in memory.
Yes, this assumes data in memory. If data is not in memory, for example, if you have CSV on the text file, we do have a CSV iterator. And for images, so most like this one is simple, but the most likely the images is not on memory. For example, you train ImageNet is fine, but the full ImageNet take 1 terabyte of data. It sits on disk. I not cover how to read disks here, but it's basically very similar. You create another iterator, which can directly give a file length each time it fetches small data from the disk, and also do all this prefetch and all these things for you.
You have support for more dynamic feeding as well, because the CSV is still very static. So if you want to generate data on the fly, more like a feed kind of thing.
So basically, the question that you want to give each time the data have different length. In this case, we would recommend to do is the record I/O. We didn't have the notebook here yet by today, but basically do that each time is a record. It's a binary format. You can push binary arbitrary length object here. Next time you can read back. So you can, this object can be of any data format. Even Python, any data Python objects can be serialized to a string. I can dump into disk. Next time I can read back. So this is a recommended solution. But CSV is kind of for simple data set. Well, because text is not so efficient. Most likely if you have huge data set and have arbitrary complexity, we usually use the record I/O, which is binary record. But in most cases, especially, you can load data into an NDArray and then you can read it. It's pretty convenient. So similarly, so I can iterate the data. So each time I enumerate the training data and the returns, actually I don't need to enumerate here for each batch in this iterator. So I counter to 1 and print the counter. So for each time for batch in data iterator, we iterate the data once. Because the current data, the batch size is equal to 4, and we have 10K data set, 10K example here, so it returns a counter equal to 2,000. So here, I tells you I can reset data set so that we can just start from beginning. So if we don't do that, actually, it will not iterate anymore. So each time you're going to start from beginning, you need to reset. Otherwise, I continue from the last point I read. Okay, so this is data. We create synthetic data and fit into NDArray iterators. So next is how to create model parameters. So for the linear regression, we have 2 models. One is W, is a weight. One is a bias. Here we know that the weight we're going to have is 2 elements. It's a 2x1 vector, and the bias is a simple scalar. So initially we start from normal for random data, and then we're going to learn this data. So we're going to create W, create a B, and the parameters we have just a W and B. There are 2 parameters. So as mentioned before, because for SGD we're going to calculate gradients with respect to the parameters, then for each parameters I attach a gradient here. So I tell the system, okay, I need gradients for these parameters later on. So I do that. So this is how to initialize the parameters. Then next I'm going to show how to write the network itself. So for the network, is simply it's a matrix times vector, which is called a dot, which is a pretty strange thing for NumPy. The matrix, the star is actually element-wise multiplication. So if you want to do matrix-matrix multiplication, you need to use dot. So given x, given input x, I only need to define the forward function. The prediction will be x times w plus b. So this is the implementation of the linear regression. So I define the function, give the input data, return the output. So that's all. So next I'm going to define the loss function. Given the predict y, given the true label y, I'm going to calculate the difference and the power 2, and then calculate the mean. So this is the square loss divided by the number of examples you have. So this is the loss function. Okay, so network loss and the parameters. The last piece is the optimizer. How to given the gradients, how to update the parameters. So here we use a very simple SGD. Given the parameters we have, given the learning rate, so then what I do that for each parameters I have, I do an in place equals to the old parameters. The new parameters we are in place right to the current one is equal to the old parameters value minus the learning rate times the gradients you have. Because we already attached gradient to that, I can access these gradients by dot grade. So then we have every piece functions we have, then we can define the training loop.
You have a predefined optimizer?
Yes, we do have all these optimizers predefined. I'm going to show you later on. So for this tutorial, I'm going to develop everything from scratch. So next tutorial will be the same thing, but using the high-level Gluon interface. So by this way, usually we feel like it's especially good for users to learn actually the algorithms using the low-level thing. You just implement from scratch, and you kind of learn what's going on here. If
MXNet doesn't contain any such predefined things. It's all in Gluon.
so.
Like optimizers and stuff.
So all this, so Gluon is the question that does MXNet provide everything here? So actually Gluon is just an interface. All these optimizers and all these data iterators are shared by all this MXNet interface. So the Gluon package actually contains less than 1,000 lines of Python code. Half of them are just a comment. So basically 5 lines of Python code. It's just a wrapper of the existing functionalities we have. So, so yes, you can get the optimizer from every the previous MXNet interface and the new interface. Yeah. So now we have every pieces we have. We can do the training loop. So the training loop here, a little bit longer. It's a little bit longer. Let me do a little bit so I can remove this line. It's too long. So the first line defines that I'm going to run 2 data passes. It tells you that I'm going to use a CPU at this time. So later on, I'm going to show you how to use GPUs and even use a list of multiple GPUs, even multiple machines. So, but here I predefined that I'm going to use a CPU. I'm going to use the movie loss. Movie loss should be here. So then, the first for loop is for each data pass. For each epoch they have, I call the data iterator.reset, which read from starting point. And then the loss is kind of, I maintain the moving loss to track the progress. So the next time, I'm going to iterate over the training data. For the index I, for each batch, I enumerate on the training data. So here is 2 lines of code. For each data is a batch data 0. I have this one. It's not necessary for here because in default data will be on CPU. But later on, if I'm going to switch a context, I can still get the thing I want. So similarly for label, I get the label. I make it into the proper device and do a reshape because I want the label to be a vector. So -1 is a data placeholder where do automatically inference the shape here. So basically, I reshape this one by a particular value, and this is given to 1. The system will inference that into a batch size equals to 4 here. So basically. So but the user -1 make life a little bit easier. Then this gives how to load data and the label into a proper device. Then I can, during the autograd record, I run the forward pass for the data, then get the output. Given the output and the label, I run the square loss. I can do back propagate. So because we record all the things, I can calculate the gradients with respect to the loss function. So then after you're done, the parameters are ready. The gradients are ready. Given the parameters, given the rate, I run SGD. So finally, the loss function, the loss function, this contains the loss value, and then I can do a moving loss equal to a smoothly moving from that. For each 500 epoch, I print the result. So this tutorial, this function shows that how to write a training loop from scratch. Basically, we first iterate multiple times. Then within the inner loop, I iterate over each data batch, and I run the forward pass. I run the loss, and then I run back propagate and update. So, but basically, this is the 3 core things: forward, backward, and update. So this is a typical training loop looks like. So then I can run it. Okay, I didn't run the previous one. I need to run every cell. So basically, you will get other thing here. So, so this is how to show developer things from scratch. Another thing I'm going to show here is the power of imperative programming, which means you actually can print. So if you want, you can print anything here. For example, I can show that the y, so y equals to x explicitly write b returns y plus b. So I can print the y. So I can print anything here. Then similarly, I can print y hat. I can print y. So similarly, you can print anything here. Then if you do that, if you run it again, I don't want to iterate too much. So if you run it again, I break until I only iterate one data batch. So if you do that again, you can print all this result from the imperative way. So you cannot do that for symbolic programming because you define network, you actually cannot access the internal data. So with the imperative, you can print anything you want. You can even using Python's debugger to just debugging into the particular line and execute step by step. So another thing here, I'm probably going to show later, is debugging. So if everything goes wrong, you actually can, for example, let me get something wrong. Print 10, I think this should be, I print a very large number here. Let me see what's going on there. So yes, so basically you will get the error trace back. So it tells you that, okay, this is output. So the first stack is, so I get error from the forward pass. In particularly, I print this line, I get an error here. So the error message is like index 100 is out of the boundary of axis 0 with size 2. So basically, the size is 4, but I'm trying to access the 100 element. So this is kind of, using the imperative is very easy to debugging. If you get error message, the Python tells you exactly where it goes wrong. You can print here, and also you can monitor all this data you have. So nothing will go wrong. Okay, so this is how to implement from scratch. The next tutorial will be very fast, which is same thing, but using Gluon interface. Basically, we put all these predefined networks and the optimizers into predefined functionalities so that you don't need to implement every time. Okay, so this is an linear regression Gluon notebook. Similarly, I import the MXNet. I use the GPU default. Data set is similar data set, similar data iterator. So now here's different. Previously, we defined network by given W, create W and X, and then I create the dense layer here. Then I create the network function. Here it tells you that, okay, we already implement the dense function. You don't need to write from scratch anymore, which means I create a sequential container and then add a particular dense layer here. The one here tells you that output will be a single scalar. So no matter the input you have, then the output will be 1. So this is the difference, as I mentioned before, compared to PyTorch and Chaos. You don't need to specify the input size. So all these parameters will be automatically inferenced given the input data letter. So we can't often use lazy initialization here. Sorry. So now I'm going to initialize the parameters. So there's a function called connect parameters, which means you define network. The layer has all these parameters in that. So the connect parameters return the dictionary, tells you all these parameters you can have. So this is a Python dictionary, and then I can initialize. In default, you don't need to do anything. So in default, we have randomly initialize a value, but you can also specify what kinds of initializers you want to have. So if you want to find control, you can give, okay, I can initialize to zeros, or I can initialize to this particular initializers. Also, I can tell you particular context I can have. So in which case you use the GPUs, I can initialize on GPUs. So as a syntax sugar, I think I can just call net.initialize. So this is syntax sugar. Similar for loss, we also define the loss. This is L2 loss. We just create L2 loss here. So optimizers, we have a trainer. So the trainer, you can tell them, okay, I'm going to use plain SGD optimizers. I tell you I'm going to use learning rate equal to 0.1. In particularly, I need to pass you the parameters I'm going to update here. So it tells you all this, I can update all these parameters. The trainer will create gradients for you and then do the previous one. So basically the trainer. So the training loop is very similar to before. So similarly, for each data epoch, and for each data we read, we record the forward pass, which is given the network, given data, and given the loss function, and run the backward. The only difference here is a trainer.step. For each step, we update the parameters given the gradients you have. In particular, I give the batch size. I need to give a batch size because the trainer actually don't know how many examples are here. The gradients are just a sum over all these examples. So here I want to divide by the number of batch size you have, so I can normalize the gradients over the number of examples. So it tells you the batch size here. Okay, so then we can run it. It's very similar to before, but here I use the high-level Gluon interface. Basically, the Gluon interface makes define the network, initialize the parameters, and define the loss, and define the optimizer much easier. So this is another thing. But you can always implement from scratch. So this is, we feel like people want to learn something. Another thing probably I'm going to show you here is what the parameter looks like. If you want to access all the parameters, so I can call net collect parameters. So it will return a dictionary. Every layer we have a particular name. We only have a single dense layer. So dense 0 is the weight. So we have a shape. This is the weight shape, and this is the data type is a float. And also the BIOS, the shape is here. So you can access, I think you can access. Let me store this one. Parens dot dense. Dense 0. Dense 0. Weight. So dense 0 weight, I can call the grade. Okay. So given a particular weight, I can get the gradient function, which is the value here. I also can get the parameter, which is dense weight dot data. Can print all this, both the gradients and the data. So you can actually get the gradients here, get the data here. You can also access all this data from during training loop. So you can also even modify if you want to. Sometimes you want to hack the program, hack the training loop. You can actually hack all this data and to give different gradients. So everything here is imperative. So everything here you can access, read, and write. Okay, this is for linear regression. So the last tutorials for the first part I'm going to show is to write a little bit more complicated, but it's still fairly simple convolution layers. And especially I'm going to show you how to implement the NDArray, which is kind of 20 years ago, but using GPUs. So I'm going to jump all this softmax regressions, regularizations, multi-layer perceptrons, and jump directly into the convolution neural networks. Okay, sorry, I use actually this runs from my laptop, so I'm gonna switch to the remote machine because I'm gonna use GPUs. So okay, so the difference here, I particularly have, I'm gonna use the GPU as a context because convolution layers is kind of too expensive to run on CPUs. So I switch to GPUs here. Because I jumped the previous one, I assume everybody kind of know what is MNIST. It's the 100 digits data set. It's an image data set. So I get the MNIST. So it will download the MNIST from the website and load directly into NDArray's iterators. So you get the train data, training labels, and given the batch size 64 and test data. So this is a nest. So convolution networks, I also assume we kind of know what this convolution neural networks has. So this tutorial shows that you can write convolutions from scratch, which is giving more ideas how convolution and the data shape works like. So a convolution layer, similar to a dense layer, you have two parameters. One is the weight, one is the BIOS. So here from scratch, then we need to infer the shape by hand. So this is the hardest thing to write things from scratch. So the first dense layer, the first convolution layer, the kernels are gonna have is 20, which is the output channel. The 1 is the input channel because this is the first convolution layers. So because the MNIST have only single channel, I use a 3 by 3 kernel size. I'm gonna initialize on the context, and I'm gonna to make a little bit smaller initialization here. Similarly for the BIOS. BIOS I actually don't need to randomize. I can use zeros. Similarly for the second convolutional, this is the input channel, this is the output channel, but again, I'm gonna use 5 by 5 kernel size. Similar BIOS. The last one, this is a fully connected layer, which you kind of need to calculate, okay, the 20, you need to calculate actually the shape, which is the input shape will be 800, and then going to map into the output will be 128. The last layer is 128 map into 10. So this because MNIST have 10 label set. So this all the parameters have first convolutional, second convolutional, first the fully connected layer, the last output layer. So this I have 8 parameters here. Sure.
So here you only calculate or define the structure. You will not define the conclusion of the function.
Yeah. I only create the parameters. I only create the weight, basically. Next, I'm going to show you how to create the convolution layers.
And what is the CTX equals CTX?
A context, so, it's a context because it's a device information. So because we're going to use GPUs here, so the context is use the GPUs. I'm going to initialize on the GPUs. So so basically, thing here, if you want to run the operators on GPUs, the only thing you do that you make the input sit on the GPUs, and the output will be on the GPU. The MXNet doesn't support in that you're gonna to if you have 2 input, one's on GPU, one's on CPU. We don't support that because we feel like people may be very confusing about that. So each time if you're supporting using a mix of CPU and the GPU memory, it's doable. But if we want people explicitly say that you want to initialize a particular device. Otherwise, people don't pay attention to that. You maybe get a very slow performance. Because something is on CPU, something on GPU, you have frequently data transformations, which is sometimes, well, we need to answer the question, why my program is slower? We need to look into that. Okay, this guy is on CPU, you need to copy to GPU sometimes. Okay, again, all the parameters I attach gradients. So the thing here is that it's similar to get the training data, the data and the copy to the context, copy to GPUs. The only thing here is that, well, actually, to using the NDArray interface to implement the convolution layer is harder. So I leave it tricky here. I just call the ND the convolution operators. I actually cannot use in the gen dot multiplication to implement convolution here. So we already implement the convolution operators here. So then you can give a data, given the weight, and given the BIOS, and given the kernel size, number of filters, then you can get the result. So this is the, okay, I didn't run.
And you assume that the size of W1 matches the rest of the problem?
Yes, so this is a potential problem for building from scratch. Later on, I'm going to show you the Gluon interface. You don't need to matter. You don't need everything about the shape. But if you want to do things from scratch, actually you need to do that. You need to guarantee that, okay, the kernel, you give the proper weight and the proper bias. The operator will not automatically inference for you.
It's still all in the documentation which dimensions should match, right? So the convolution operator.
Yes, so document, let me see you the document. We actually spent a lot of time a few months ago to convolution. So it kind of, well, yes, it kind of tells you the data will be batch size, channel height wise, and the weight will be number of filters, channel kernel 1, kernel 0. So this is kind of, it's usually long document. And so you have also 1D convolution, 3D convolution you can do as well. So yes, you can find all this in our website, mxnet.io. So I'm going to show you. You go to mxnet.io, then you can search convolution. So for example, I can, maybe I can, so basically you will give all the previous document, but there's kinds of more, it's the, where's my link? Yeah. So basically a little bit more readable format here. But this I show the low-level interface. It's for education purpose. In most cases, you don't need to use this low interface. I'm going to show you the Gluon interface later, make life easier. Okay.
Just a question about the flexibility. You said the Keras, for instance, it removes some of the flexibility of TensorFlow. The Gluon, how much does it retain the flexibility compared to using MXNet?
Okay, so the question that how Gluon have the flexibility. Well, yes. So Gluon have two interfaces. The current interface I show you is sequential. Each time you add a layer to that. But if you remember the previous slides, so in the PyTorch, so this is PyTorch ways. You actually initialize operators by yourself, and you define the for function. So you have flexibility to write all these for functions. We have the exact same interface. So you can write, you want to do more fancy stuff for the for functions, you can do that thing here. So even that, you can implement operators. You can use in the low-level NDArray interface, because in the NDArray have auto-differentiation. You can use NDArray interface to implement the operator here, and then you can call this high-level operator later. So this is kind of, you have more programming interface. You have two different, so basically three different programming interface. The first is sequential. You add all the things there. This is good for very simple structured networks. So the second interface is here. You actually define the for function using this atomic linear ReLU and the convolution thing. The last one is actually using the NDArrays to write operators. So this is also just to build things from scratch. Okay, so this convolution, and then pooling. Pooling is similar. I can call the pooling data and tells you, okay, I can use max pooling. I tells you the kernel size, strat size, and then I can tell you the shape. I also can print the data as well. But it's a lot of data here. So activation, we can actually implement the activation function here. The ReLU basically, I create 0 matrix, which is copy the same shape context from X, and have the maximum X and the 0. So this is ReLU. Similarly, we can implement the softmax from scratch. Given the output, I do the exponential and the sum and exponential divided by partition. So the thing here, I divide by max. This is a common interview questions. I think it's a common interview, coding interview questions, how to compute the softmax. Usually, when you do exponential, you need to minus the maximum value here to guarantee that every number is a negative number. Otherwise, if you have a very huge number, if you have 10 or 10 is fine, you have 100, do EXP, you can maybe out of boundary. So you get the infinite number, then you divide, and you get a lot of number. So by minus the maximum value, you guarantee everything should be negative. So max value will be 1. The worst case is you get a 0, but 0 is fine. Because you cannot, you sum 0 because you need to sum the exp result later. If you have 0, that should be fine. But if you have 1, if you have infinity, then divided by infinity should be a problem. So this is a little bit tricky how to implement software. Yeah, questions? So sorry, you want to reshape by? Why I want to do reshape? Well, then the easy way that you can actually print partition.shape. So I can call softmax. I give ND zeros. I saw shape equal to, I saw batch size equal to 5 and the input size equal to 3. So you get the partition will be 5, and then you get the error message. You divide. So basically it tells you okay, so this is a little bit so that this 5, the input, here is 5 by 3, but this is 5. You actually need to add a particular 1 here to get the broadcasting working. So by reshape here to here, that you add the particular access into netter, so that allows you to broadcasting. I think we should fix it. This is a little bit tricky. I think we can fix it later. So then that should be fine, because reshape add a particular 1 here, then the shape here. So basically, I can print. I print. I print the shape. So you can print every shape here. So this is kind of imperative to let you to debugging much easier. So now we can define the model here. So the network, given all these parameters I have, so I can chain all this convolution, ReLU, pooling, and the convolutional ReLU, pooling, and a flat. So because the last one, the convolution output will be 3D NDArrays. I can flat into 2D, then I can fit into flick connector layer. I can flick connector layer just a dot between H2 times W2 plus B2, B3. So the tricky thing that you see that I print a lot of shapes. This is because if you do things from scratch, you need to carefully manipulating all this shape information. So I'm gonna run it. So now you can you can enable the debugging model, let you print all these shapes. So you have a basic idea what the shape changes between the convolution layers. And finally, the output will be given 64 is a batch size. This is finally you can reduce until you get 64 times 1. So I can remove all this print here. Otherwise, I print too many informations.
I have a question about the visibility and the print. You talk about printouts a lot and so on. But if you define calculations on the GPU and you want to run a debugger, like for instance, you're using Python, can you put breakpoints in halfway through the graph and look at the variables that way instead of work? Is that part of the printout?
Yes, the problem that if you want to print, I still print EXP, but if EXP is on GPU, what happens? Actually, you can print as well. For example, I create zeros. In particular, I context equal to GPU. So I can print actually on GPU as well.
Yeah. But can you put the breakpoints? If you're in Python, instead of some other IDE, can you put breakpoints inside the calculation?
You can. So the question that you can breakpoint. You can create breakpoint on the Python code. That's fine, because Python actually we override the print function so that Python can actually print the actual result. The only thing that, well, you have overhead because you copy data from GPU to CPU. But I think it works well. But if it doesn't, please issue a bug, we can fix it. Because I personally did. Yes, so I think the basic idea, we definitely need to guarantee that it's working. I don't think technically there's a problem, but if it doesn't work, please raise an issue we can fix, because I personally, I only print. Okay. Yeah, sure. I just turned from a Python programmer into, I just turned into a C++ programmer to Python a year ago, so actually not so familiar with the Python tool chains. Why? Okay. But then, okay, I can run it. So I defined the cross entropy. Similarly, it's log to the predict and the element times the true and the sum and get the minus here. I tell you I can sum over the the first axis here. Similarly, I can create evaluation accuracy, which is for each data batch, basically run the forward pass. So similar to before, but this is not necessary. Similar to before, then I do the argmax to find the prediction and to sum actually the prediction equal to the labels. So I get the number of correct and the number of examples I have, and then I returns divided by number of correct the examples and the number of total examples, and return as a scalar. I can return a normal Python float point. So this is get the accuracy. Then everything we have. So here, I don't need this line. So here, the train loop is very similar to as before. You give a data, you iterate over epoch, you give a moving loss, then you reset the data iterator, you copy the data. Here, because I use GPU, this is necessary. We need to copy data into GPUs. I run the forward pass. I run because I run the cross entropy output to the, oh well, do I need that? Okay, then, okay. Then I backward propagate, I run SGD. So I print the moving loss. I finally evaluated the test accuracy, training accuracy. I can show you something. So basically, you can run it. It take a little bit longer. It take about 4 or 5 seconds on this. I use a very small, very old GPU. The G2 instance is like 5 years ago GPUs. So take 5 seconds per epoch. So you can, for each epoch, I print the loss, I print training accuracy, and test accuracy. So that's all. So yeah, questions?
How can I use both CPUs if I want to use CPU?
Yes, the question is how to use all the CPUs. So the easy way that you can, using GPU 0, because if I want to use GPU, and then you could GPU 1. So you can change it basically using all GPUs. I'm going to have a detailed tutorials how to actually implement multi-GPU training program from scratch, and also how to use in the Gluon multi-GPU interface. But in short, that you can just give a context to a list of GPUs going to use. So this, yeah, question.
So up to this point, everything is kind of looks very similar to PyTorch.
Mm-hmm.
All the narrative programming. And,
Yeah.
So I was wondering if the difference is more subtle, or maybe in the backend, or yeah.
So the more difference. So I mentioned before, this new interface is followed from PyTorch closely. PyTorch also follows from Channel closely. We also, the tiny little bit difference for the interface aspect is like the layer definition. We actually follow the chaos, but it's very similar. The more difference is more like on the back end. I'm going to show you how the multi-GPU distributed training, and also another very key aspect that we can get a symbolic definition from it. So given all these networks, I can get the symbolic, get the coding symbolic program from it. So this is what I call Gluon. It's actually mix all this. So this interface for research, faster research development, but later on, you care about performance, you want to portability, you want to get the symbolic executions. So this is one key thing. So for Facebook, you know that Facebook research is using PyTorch, but Facebook products using Caffe 2. Actually, this new interface trying to group two together. We don't want you write another language using for research, and then you want to deploy into product, you need to rewrite it again. So. We did, but it's usually not a good idea to put on the front page. We are faster compared to others. So we're trying to, so we actually did the TreeLSTM, we are kind of 50% faster compared to PyTorch, because TreeLSTM is an example to show the power of imperative programming. Again, I can, later on, I'm going to explain a little bit later why we are faster. So it's more interesting. So lazy evaluations, auto parallelisms. So this makes things faster. And also symbolic, trying to cache all this computation graph makes things faster. I'm going to explain on the next part. But here, the last tutorial I'm going to have for the first part is to, again, how to implement CNNs using the Gluon interface. So, okay, very similar thing. Data. The only thing here, well, this is a different thing. We use the sequential, again, the syntax sugar. We can add a bunch of convolution here. So basically, create a net, add a comma 2D. But now we don't need to worry about the shapes. It only tells me, okay, the output channel will be 20, the kernel size will be 5. You can also tell me 5 by 5. You can change to a different value. So in default, you will be 5 by 5. So, but you, for simplicity, tell 5. Then give the pooling layer. It tells me the pooling size will be 2, the strata will be 2 by 2. Again, another convolution layer, output will be 50, kernel size will be 5. All these convolution layers, I added the value after that. So I flatten into a 2D and create a dense matrix. So this is basically the previous convolutional definition. Yeah, question?
Maybe you said that and I missed it. What did actually mean and sequential?
Oh, sequential. Sequential is a syntax sugar. So given a sequential, it's like you can think a queue. You can add all these layers one by one into the queue. So basically, later on, if I want to forward pass, I feed with the data, I run this networks one by one. So basically, the output of the previous one will be the input of the next the layer. So this is what sequential means.
So if you, what are the other options? If it would be recurrent network, it would be something else? Or?
Recurrent, you can also have sequential, because currently you can recurrent network, you have time, you need to not do the thing, but you can just add SDN. So currently we can, RM package, I not show these things. RM package is very similar using sequential to have it. But you tell me how many LSTMs you have, then that's enough. So because in imperative, given the different data lengths, I can unroll it. I can run according, I can run the LSTM on the time aspect, depending on the data you have. Yeah, question?
For Google and for instance, you have a separate branch of those inception modules. Can you use sequential for that?
No. For in that case, you define the inception block. You basically define the inception layer. It's a huge layer actually. Internally, you use the previous PyTorch where you write a forward pass. You create a new layer called inception layer, and you write using the forward pass. You can define this all the things. But then, if at that one, you can add this sequential together.
You can use that API inside the
Yes. So basically, you add, for example, add my inception block. So if you have this one, you can implement a class. Basically, what you do that, class my inception block, which is dot block Gluon dot block. You define the forward path x. You need to initialize something, then blah blah blah, then you can add back. So this is kind of thing.
Can you also define for a while using the sequential and then let's go define a few more layers and then define?
Yeah, basically you can have a while. Basically, this is how we implement the LSTM for loop, LSTM cell. So there's an LSTM cell, which is kind of for I in range length x, kind of if the first dimension is a sequential sense, I blah blah blah. So this is basically how we implement LSTM cell.
That's not quite what I meant. I meant if you said net Gluon and sequential, then everything in NN must be sequential, right? So if I want to use the sequential notation for a while, and then I have something which is extremely non-sequential, I want to keep adding to the net.
Okay.
Maybe want to finalize with the sequential section again. Is it possible to mix and match this?
So in this case, I think part of the result is sequential, part of it is not. So then, yes, you can do that. So basically, so I'm going to create another example here. So for example, I define the sequential net. I can write another thing, my fancy net. So basically, you initial define the init something, self, something. Then self.net.init. So basically, you copy this one into here. Later on, you can do a while loop. You can do a for loop net x. You can chain everything together. So basically, you have all the flexibility how to hack all these things. You don't need to worry about anything. Basically, if you can run in the Python, that should be fine. Okay, so this is sure. Yeah. We don't have a parallel actually, so. So yes, so sequential is a very limited but convenient inference. If you want to write things in parallel, for example, so this is network. You need to read this way. You need to write this way. For example, this self net 2 equals to net. For example, if it's a function, I create a new one. Then the forward pass, I given y1 equal to net 1 self dot net 1 given x, and the y2 dot still run in parallel, but you need to write by hand. And for example, why do you y1 cat all these things? Basically, you have given the x to net in parallel, and then runs and cat the result later on. So then we don't have a parallel sugar for that one. Actually, you need to write by hand. But the beautiful thing here, I'm going to show later, the system will automatically parallel all this thing. So for example, these two guys can run in parallel, the system will know that because there's no data dependencies. So this I'm going to show on the next part of the tutorial.
So you mean the system will optimize this one in the MXNet?
Yes, the MXNet backend engine, because you know that run network 1, you only need x. Network 2, you only need x as well. So these two guys have no dependency to each other. So we can try this guy can run in parallel. So, but later on, you need to wait until these two guys are finished and they get a result. So, you mean the low level optimization? Gluon we are not doing. So Gluon, what Gluon do is like, Gluon push all these operators into the backend. So the backend could be automatically optimized for you.
So rely on the backend, like MXNet.
Yes, yes. Okay. So I think I just want to, so all these other things are very similar. Connect the parameters, initialize. We have a softmax cross entropy. We have a trainer SGD, and then everything is similar. So I'm not going to explain all the things. But the key message here, use a sequential. You don't need to worry about the data input shape. You can easily define the chain a bunch of layers. But if you want to do fancy things, you can actually arbitrarily mix all these sequential layers, and you write your own follow-up functions. So I think we can have a coffee break. So let's on. We started like a half hours later. So questions?
So you said Gluon is like 500 lines code. So how many keras, interfaces, and layers does Gluon support?
I think we supported all this chaos interface. Let me show you. Gluon. Well, probably just to go to the website. The mstat.io, there's APIs, Python. There's a Gluon package. You can get all these layer definitions here. I think we are trying to get all these major chaos layers there. But I don't have a particular number how many percent we covered, actually. So any questions? Yeah.
Do you support or do you plan to support the model interface in Keras where you can define graph structure models without worrying about the input shapes?
So we can run chaos actually. We support the whole chaos front end. So
Gluon provides that capability where you can define a graph structure network and it does the shape influence thing.
you mean provide a chaos model-like interface? And okay, so you mean you're gonna have model.feed, something like that?
That's more like you define a sequence of operations where you're going to have parallel paths or a graph-free structure for the network.
Mm-hmm.
And in Keras, you can just create a model by specifying the input and the output.
Mm-hmm.
And then it creates the model for you. So it's like more advanced version of, you have a sequential container.
Mm-hmm.
Or something like a graph container.
Well, we don't support now, but we can add it back. If we think it's useful, we can add it, actually. Yeah. Okay. If we don't have questions, we're going to have a half-hour break. We can ask questions here. Then we go back at 11:30. I'm going to quickly show how to write things. Basically, very quickly go through the advanced topic about how to get a symbolic from the imperative one and how to write a multi-GPU thing. I think I'm trying to squash everything to have our later on. Yeah.
Maybe just do get like a report class. I don't want to squash it too much. I think that's the interesting part.
Okay, so then because we only have 1 hour left, so well, if you want to go forward, I can do that. So how about you feel? But I think the next part will be more interesting, more advanced topics. But this is more like, if you're not familiar with the interface, it's kind of a wrap up. But yeah, let's do let's start at 11, so then we can have enough time to cover the more interesting stuff. Yeah, sure. Hi. Oh, nice to meet you. So we talked to, actually we talked to you guys before.
Yes, you might talk with Eve.
I think the new PE you have, I think I talked to one of the PE you have in Symbolic.
I'm principal research scientist, so I'm not sure which one you talked to, but So we are currently using mainly as a firewall, using YOLO on top of .NET, but we really want to try to play with MXNet and see. So we played a bit, we tried some demos, some of them worked for us and some of them didn't. So first we wanted to ask, is it possible if we have some technical problem to contact you?
Oh yes, we do have MXNet as user at Amazon, the email list. So this is pretty active. I think. Let me send you. So we have MXNet-user at Amazon.com. This is.
Yeah, I'm open on the network now. So it's MXNet.
MXNet users dash.
Like that?
Added dash between MXNet. Oh, no dash. At Amazon.com. We have a mail list for that.
Oh, mail. Okay.
Yeah. So I think we have.
I'm not on the network now, so it's not going to work.
We have a particular thing you may be interested. We have a compiler which can optimizing the ARMs or even any chips you have, so that all developers can compile into the particular hardware, which is very optimized.
Yeah, right now we use the Jetson X1.
Yeah.
Yeah, okay, and one, so I don't know if you want to do it now, but I just tried on the fly to run these tutorials. And then before that,
You probably, it's a low version of MXNet. You need to install 3 //3.
okay, so let me
Probably uninstall MXNet and then install the
So what I need here is, I won't get it now, but yeah, so I was installing, you say that's here, so I was installing this one, but then when I did that, I got message that it's already installed, because I probably
uninstall it first, then install that.
So how you uninstall it?
Pick uninstall MXNet. Yeah, that should be the right version.
Okay, so I'll try to set it initially. Okay, so now we can.
You're gonna restart the Jupyter kernel.
Okay, thanks.
Hey, guys. Hey. Hey. Yeah, sure. Yeah. Oh. So I worked with Joe for a while. It's a new one, so we're trying. This is a new one we're trying to push internally and outside, because the previous one people still think it's a little bit harder to use. So this new one will make people much easier to use. Yes.
All right, thank you. So who's the person? Is it me? Who's helping you?
We do have a bunch of guys actually. Yeah, we do have a private.
I can look it up once I get back.
Oh, that's nice.
Yeah, this is fantastic. I really have to tell more people in video about Gluon. Did you just announce it?
We didn't launch yet. It's a pre-release. So we're trying to launch. We are writing a book, so also
Yeah. So,
trying to get ready in the month.
do you have a technical writer too? Because I was on your docs.
We do have now. We do have.
Now you do, okay.
So he's a CMU professor actually.
Okay.
So this is the guy you work with.
This guy, Mark, he's really good. This guy's
Oh,
really
yeah,
good.
he's really good.
Okay.
So this guy.
Oh, so you have nice.
We have this guy, unfortunately, this guy was on a car accident.
Oh, those are good guys. Yeah.
He's really good. He works really on the FP flow.
P6.
Very good guy. You guys are pretty good, actually.
Oh, that's good. Okay, yeah. I'll read all the docs.
So, control magic and dynamic going into.
Oh.
So I have one question. So I just checked the model design, and I don't really see there's a lot of prepared models for MXNet.
Oh, we do have a bunch of, so we're going to release it. So we have a more Gluon model package released soon. So gonna check the recorder. Recording thing. So we're going to have a bunch of, so we have a pre-trained model on the full internet and also the MXNet.
So I just checked the MXNet.
Data.mxnet.io. So we have this one. This is very useful if you want to fine tune. So just train on 20 minute images. People tell for fine tune much better compared to the model train. So this is probably the one I'm going to have to try. So take 200 GPUs for. Oh, you're back. Maybe you can just just try yourself. So since it's going to be used, you can make sure we got it. Yes. Gonna have a power. Oh, eBay. Yeah, we have Hassan from eBay.
I wanted to ask if you can override like the auto like application. Like let's say that for some reason I have like a better optimization for a second layer, and I don't want to use like the auto differential.
Then you just are using. You can just write the backward pass.
So I can just write the backward
Yes.
pass. It will just ignore it.
Yes, it's override. I think. Default the backward pass. We have a default backward pass basically called the backward, but you can override it. I think. Yeah.
So for the backward pass, I'll want like to I'll get like as an input a tensor for the previous layer, and I'll be able to.
Yes, you basically and the output packs give the head of the gradients, and that should be fine. Yeah, you return the. You need to write.
For each layer that I'm not writing it, it will use the default differentiation for this.
So that's a good question. So probably we have a customized OP tutorials. We didn't. That tutorial.
Thank you.
Yes, on the Gluon.mxnet.io. Hey guys, let's start it. So first, I give a very brief introduction for what we do for the backend optimizations. So from front end, we're supporting Python, a bunch of other programming languages. So then the backend on C++, so it will construct the computation graph at the backend. So all this in parallel, we construct the coding computation graph there. You can do a bunch of optimizations. I'm going to show you some basic ideas. Basically, how to use it. So for example, I show the first one as I do B, C, and D at the when you calculate D, I know that A is not used anymore. I just deleted the memory of A. So similarly, if A is only used by B and the B is only used by C, we will try to share A and B's result. B. So this is very two memory reduce. We can reduce about 2 times for training and 4. This have no cost, so this is a computation graph. The other thing I not go very deeper for that. It's like you can trade off. So basically, the basic idea that for some I don't need to store the forward pass. For the I can recompute the results. So I trade off computations. I'll show you an example here. So if the layers use the complexity to square root of n. So I can show a particular example here. Mm-hmm. So I know the basic idea that to several plots, and each time we pick the forward pass. So I give a basic idea example here. If you run ResNet using batch size 32, so if you don't do things, or like you need to over 100 bytes, then if you're using the previous thing, you just you can fit a ResNet using a distant batch size 32 for training. The overhead, you pay additional 30% of overhead. You have even a single small GPUs, you can run 1,000. Then, well, you need to be slower. Then you have no free lunch.
So are you saying
to specify a tag called automatically. So you cannot do by hand, actually. Yeah. Yes. So when you start MStat, variable tells MSNet we use that. Also, you can algorithm. You tells me, okay, I'm gonna use the either then it will be enabled. Only run Symbolic, but later on I'm gonna show how Symbolic. So this is only for Symbolic programming. Oh yes, so memory optimization is independent of hardware. It's basically, yeah, it's not related to hardware, but it's basically a computation graph optimization rewrite.
So could you utilize that even if I run in an embedded system which has very specialized hardware, so I can still utilize those optimizations?
Yes, that's true. But that's only for training. For inference, that's easy. For inference, you can do much better because for training, you need to store the forward pass result. For inference, life is much easier. Yeah. Okay. Another thing that you can do that is a fusion. So for example, if you write add and do a so you first do a multiplication and do add. People write A times B plus C. Yeah, that's a normal way people write things. But actually, the system is able to fuse these 2 operators into a single one. To a fifth operator, because for basically you generate a single CUDA code, for example, then you see NVIDIA will have FMA instruction to optimize it for you. In particularly, this is a little bit problem. So the add-on I mentioned before, the add-on optimizers have probably 30 lines of code. Actually, we can fuse this add-in, all this element-wise operator into a single kernel, which have potential 20% of performance improvement on the ResNet. So in this case, this all happens automatically for the backend because I'm going to show you why we can do that because of lazy evaluations and also can turn imperative into symbolic. So you can generate the code on the fly and do using a media runtime to get all these things done. So this is a very brief introduction. So I'm going to show the notebooks actually how to convert in symbolic and converting from imperative to symbolic. So it's called Hybridize. This is why it's called Gluon. Let me show this right. So we see that we use a sequential before. Now we're going to use, there's a called hybrid sequential, which makes this all this imperative and symbolic. So this is very similar to before. So this only difference that you add hybrid before sequential. The reason why we don't have hybrid for the default sequential because this is kind of the one topic. We don't want to beginner user to worry about that too much. So here, each time I create a return, I get 2 dense layers and 1 dense output. But the only difference I have hybrid here. I connect the parameters I initialize, so this one. So then I can run a simple forward function. This is get a net, get a x, and then run the forward. I can say, okay, this is the output of it. So that is as normal as before. But now the trick here is that you can call hybridize. When you call the net.hybridize, which will turn automatically internal into a symbolic execution. So here I can, people will not see different, but the internal system, we are trying to hybridize it. So here is nothing different here. Same result as before, same thing, same called net.x. So simple click and then get the symbolic. So now we compare the performance. So this benchmark function, each time I call the start, I repeat the network for 1,000 times. So because MXNet uses lazy evaluations, so you need to you want to benchmark things, you kind of need to block MXNet until you get the result done. So I say, okay, I will wait until Y is ready. So I return the time. So now I create another new network, benchmark it, and hybridize it, and benchmark it. Well, you can see that the time is different. So no hybridizing is used 0.8 second. After hybridizing is using it's basically 2 speed up here, 2 times speed up. So let me run it. Well then, oh yeah, the result different, but you still get kind of 2 times speed up here.
And you can train with a hybridized or?
Yes. So no difference, but I'm going to show the difference later. But most cases, no difference unless you have print on this forward loop.
Can you train with the imperative mode and then hybridize after when you have your finalized network?
Yes, you can do anything you want. So you can. So I'm gonna explain the details between the letters so you will see what the difference later. So the only thing for hybridize is like you lose a little bit of you lose a little bit of flexibility. So if you want to print on the 4 paths, it doesn't happen anymore. I'm gonna show the details later. But another thing that I'm gonna show you that how to get the symbolic program. So previously we only feed with actual data, NDArray data. Now we can actually give you, okay, I don't want to give you data. I give you a placeholder. It's a variable, which I can get data later. So then I can print x. So the x is not anymore data. The x is a placeholder, is a symbol called data. It's a symbolic variable. It's a data holder. Then I run for the pass. What is y? Y is no longer the result because we don't have data yet. Y is another symbol called here. And I can call y to JSON to get the code in JSON definition. So I print only a few lines of code. So it's pretty similar to Cafe's product buffer definition, but now it's a more JSON format. So using this model, so this is define the whole computations here. So in this case, you can just use this JSON file and get rid of all this Python code. So later on, you can save directly into a JSON format. You can dump the parameters into a binary format. And using these two guys, if you use MXNet before, you can use at any front-end, C++ or Scala front-end binding, you load it directly. You can get rid of Python, and you can deploy, you can get the portability. So basically, after Hybridize, you get performance improvement, and also you can dump into a language-independent format you can load into. You have portability. So these are two potential benefits. It's also the major benefit for symbolic programming. But next, I'm going to show you what is the cost you pay. You actually have no free lunch. If I can do that easily, then I can enable in default. But unfortunately, no. Something I'm going to show you why it's not a good idea. So here I'm going to show you. So this is previous. I used a hybrid. I used a sequential syntax sugar. Here I'm going to implement, and I mentioned before, I implement on the block style, which means I create a customized layer, and I can do anything fancy things I want. Here, I initialize it. I initialize 2, 3 dense layers. Dense 1, dense 2, dense 3. So this is the output size of dense 1, output size of dense 2, output size of dense 3. Again, here, you don't need to specify the output, the input shape. So system will do automatically shape inference for you. So this is a potential benefit using the Gluon high-level interface. So now the forward path is no longer called forward, it's called hybrid forward. So the difference here, the input is X, but different here you have F. What is F? F is a function space. When the data is NDArray, F will be NDArray. F will be NDArray. But if X is a symbol, F will be the symbol. So this is imperative. This is symbolic. So here I'm going to show you what is type X and what is F, and given X, I do fully connected layer and do ReLU. So any function, any operators in MXNet are registered on both NDArray and the symbol. They're identical. So they're the same C++ code, but the only difference is that NDArray take NDArray input, but symbol take symbol input. So you can do, given X, I do fully connected layer, I do ReLU, and then ReLU is a function defined on the ND or symbol. But FC1 is here, it's a dense layer. Dense supporting both imperative and symbolic way. Then given X, I get FC2 and ReLU and FC3. So this is what we have. Now I can run it. Now I can show you that I create a net, initialize, given the data, I run first time, I run second time. The first time we show that the type of X is NDArray. The type of F is function space is NDArray. So and the second time I run this function again. This function is called again, then get it. So now what the difference if I call hybridize? Still get the same X, still get the same X. So as we know that the Y will be the same as before, so we get the same result. But internally, it's different. I'm going to show you. What's my? So the first for loop, the type of X is a symbol, actually. So I first create a symbol, and then I copy this data, bind the data into the symbol, and F will be symbol. So this is first different. Everything's converted from the NDArray function space into the symbol function space. The more interesting thing here, the second for loop is nothing outside, which means this function is not called again. This function doesn't run on the second pass. The reason is because for the first time I'm going to run it, the system will construct the computation graph at the backend and cache it. Second time you run it again, this function not be called. I just call directly into computation graph. So you can see the benefit here is that I no longer need to run this Python functions. Everything is on C++. So, and enjoy all this memory optimizations, all these things I mentioned before. But the potential problem that if you print something here, the print is not running anymore.
This is only for the hybrid forward. For the ordinary forward, you get the print.
Yes, it only works if you call hybridize. After you call hybridize, the functions only be run once, it not be run twice. So this is why we get faster. We can get all this off Python front end, and also we get the portability. But okay, you lose the flexibility. If you want to print, if you want debugging, sorry, it doesn't work. Otherwise, you need to use a symbolic way to print. It's harder. You can get the symbolic print operator to get actually thing, but it's not so straightforward. So the recommendation here is that for debugging, for development purpose, you use the purely imperative. But later on, you find, okay, the program is correct. I can run on larger scale on MXNet. I want to deploy, just call hybridize, and you will get a symbolic definition, enjoy everything symbolic you have. So basically, programming with the imperative way and deploying using the symbolic style. So this is kinds of recommendations we have. Okay, any questions here?
If you train all the time, and when you're done training, you have it defined in terms of the imperative way. How do you convert it after? You just replace all the functions with a hybridized version.
The weight are the same thing. The weight are still there. You can access. The only difference that you cannot print any. So the only difference that the default function is not running anymore. But all this, how to get the parameters, you still get it. So all these functionalities are there. The only difference that you can, for the path, you cannot print things there. But you want to access the parameters is still the same thing. So the only thing that we just catch this part of graph into the internal C++ computation graph format, and then everything else is actually remains the same thing.
They're different networks, right?
Yes. Sorry?
So, I mean, you define the net with the hybridized.
Yeah.
As it's for now. If you train without the hybridized, and then you want to make it hybridized after training.
Yeah, that should be fine. No, nothing different.
How do you change it in hybridized?
Are you then? So, for example.
I have my weights. They're trained fine, and I just want to deploy it now. But I have to work in the
Okay, got it. So basically, you can train with imperative, and you want to load the letter. You can load the parameter. You can initialize so basically you can initialize the parameters equal to the previous one you have because you already trained, and then you let the hybridize. You can got it. Yeah. Okay. Hybridize. Yeah, basically. You can call anytime you want to. You feel like it's ready to symbolic. You also don't need to call anyway if you don't. The performance are fine. The major thing is the memory reduce actually. The performance in normal network is like a 20 or 30% of thing. But we're going to release another major refactor of the backend. We'll make it much faster. I think we're going to make it 50% faster, especially for complex networks. So okay, in the last half hour, I'm gonna to very briefly introduce how to do parallelizations using multi-GPUs and multi-machines. I'm gonna to first give basic ideas, how we did things, and then I'm gonna implement things basically from scratch and using the Gluon interface. So writing parallel program is pretty painful. Even that you have only 2 finite connected layers, so this is a dependency graph between if you run on 2 GPUs and single GPUs. So you need to resolve all the data dependencies, and you're trying to find a way to parallelize it. So, so that we're trying to fix it by the backend engine. We are using lazy evaluations. So import MXNet, you create A, C equals A something, B equals A plus something, D equals B times C. So actually, until this point, I can, sorry. I'll probably add another thing here to beta. So basically, this program is not executed until we call D wait to read. You just push all the operators into backend, or you call print D. You print D, you need to wait until you execute it. So the backend engine will construct the coding computation graph. So this shows on the right. So it knows that, okay, C and B can have no dependency to each other. So you can run things in parallel. So this is a backend engine will do that for you. So it's guaranteed correctness, but they're trying to find every possible way to parallel that. I'm going to show in the tutorials how it actually works. So another thing that if you're going to write your multi-GPUs, a typical way we are using is data parallelism. So given examples, it first partition the examples into multiple GPUs. For example, if I'm going to use 4 GPUs here, I partition into 4 parts. Each GPU will get 1. GPU will get the weight from something called key value store. It's a distributed key value store. You got the weight, got the parameters, and the computer gradient using my local data, my local parameters, and then I can push the gradients into the key value store. The key value store, we aggregate those gradients and update the weight. So this is how data parallelism works on here. So how to change to distributed computing? It's very similar. The only thing that, okay, the examples is on a distributed file system. It's not on local. GPUs happens on multiple worker machines. So each machine will have maybe 2 GPUs. And the key value store actually maybe also spans on different machines. So
Distribution for each computer is automatic, is it? Or you still use the key value thing?
yeah, it's also key value store. So
If you have just one PC with like 2 or 4 GPUs.
yeah, that's same thing. Yeah. So so the only difference that only this communications happens over network. But the nice thing I'm going to show you later, people don't need to worry about that. So system will automatically communicate over the network. So I'm going to show you a key thing we find is like, I got to briefly mention it. So the key thing find that local GPU to GPU have faster communications, but they have much slower compared to GPU to CPU, and the GPU, CPU to another network. So you can see that there are 3 hierarchies here. Each one, you can reduce the bandwidth by 4 to 10 times, which means we really want to make the communication happens locally rather than cross everybody talk directly from GPU to CPU. So basically, we're trying to do that. We first aggregate cross GPUs, and then aggregate the result and send to CPUs. So this kind of optimization we automatically did. So I probably not to go very detailed that. I probably more focus on how to use it. So can I show you examples? ImageNet, 1 million images with 1,000 classes. ResNet 152 use a EC2 instance. Each instance have a 16P, 16 GPUs. So they are aggregated by such style. Mini-batch SGD, synchronized updating. So we guarantee that multi-machine training is as the same thing as single machine training.
And there is no problem with if you have different size GPUs and so on. I mean, if you have a non-homogeneous system, so a small GPU on one machine, a big GPU on another, maybe 3 GPUs on one GPU.
So the question that when each machine have different kinds of GPU or even different number of GPUs, what you can do, well, usually, for example, you can roughly estimate GPU A is 4 times faster compared to GPU B, and when you partition the result, given 4 times, each time you give GPU A 4 examples, or you only give GPU 2 1 examples. But you can benchmark at the beginning and know the difference and how to partition the data according to the computation power you have. Yes, you can also need to know. You can also need to know the GPU power and how many GPUs you have. Then you when partition data, I'm supporting a load list, kinds of each load that you're going to specify to each GPUs. So, So here I show the performance result. I increased the number of GPUs from 8 to over 100. So this is a communication cost. Just no computation, just a synchronized gradients. You can think like, well, if we go, there's a big jump from single machine to multiple machines and go and decrease linearly. Then what I'm going to show that, so this is a total cost for using batch size per GPU equal to 2. You can see that, so this is the leftmost triangle point is the purely computational overhead. You don't have synchronizations. But then you increase the number of GPUs, you see that the communication costs dominate the computations. Now the total cost is dominated by communications. But then you can do that. You can increase the number of batch size, which increase the computational overhead for each batch. You can see that, okay, when you can given each GPU a batch size equal to 16, now you don't see any problem because the computation overhead is larger than the communication overhead. The backend system can automatically parallel all these communications and computations, so that then you can using 128 GPUs compared to a single one, you got over 100 speed up here. So the key message is that the computation should be dominate the communication. Secondly, the system is automatically parallels that for you. So this is only for the performance. So the more interesting here, how for the convergence, because now you increase the GPU size, you increase the batch size. Sometimes it slows down the convergence rate. So let's see the first line first. So this is number of epoch, and the y-axis is the top one validation accuracy. You can see that batch size equal to 256. You each time epoch 30, you decrease the learning rate. Epoch 60, you decrease learning rate, and finally you get the thing you want. Then, what happens if you want to increase the batch size by 10 times? What we find is like, well, yes, you little bit slows down the thing, but if it increases the learning rate, then everything should be fine. So here, I increase the learning rate by 5 times. What happens if you want to go even larger batch size? So again, you can increase the learning rate by a larger value, and especially I keep a larger learning rate for a longer time. I reduce the learning rate at epoch 50 rather than 30. So finally, you will get the same thing at the end. So as a result, compare this convergence rate result and the performance speed up, what you can see that well, training on the ImageNet to achieve top one 22.5 accuracy, using the 8 GPUs, it take about a week. By using 80 GPUs, you can within a single day, and even increase the ladder, well, you can control everything in half days. So this is result on GPU EC2 P2. This is K80, it's very old GPUs. If it's new one, Pascal, and especially Wata, a media new one, you actually can control within an hour. But we think that, well, half day is good time, actually. You don't need to make everything into a single hour. So because, well, you can launch the job and go home, and next morning you can check the result. So this is the kind of thing you want. Then by half day, you mean that you can increase the training data a lot. For example, using the Pascal, you can use the full ImageNet. It's like a 10 million data set, 10 million images, using 100 P100, then you can still control that everything happens in the single day, in the half day, actually. Yeah, during night. Yeah, question.
So as your single node performance increases, do you expect to see a different set of network latency curve? Or in other words, do you expect to maintain the scalability advantage as your single node performance increases?
Yes, the question that when the GPU computation increases, then you given the same batch size, you actually can communicate more within a single time. So then you give more pressure to the network bandwidth. Currently, if you use P106 to K80. Basically, it's 8 physically K80 in a single box. The network bandwidth is like 4 gigabit per second. So, but if you change to P100, you can kind of improve the performance by 2 times. Because P100 only have a single GPU, but here you have 6. So P100 you only have 8 GPUs per machine, but here you have 16 GPU per machine. So P100, you increase the computational power by twice, roughly, and then the network bandwidth is almost like 8 gigabit per second. But 8 gigabit per second is still not so high. But if you change to water, yes, you get 20 gigabit per second. You kind of need at least a dual 40 gigabit Ethernet, kind of. But another thing that you have data I/O also requires more data I/O speed. Okay, so I give a very fast track of what the result we can get. So next I'm going to show you actually how to write multi-GPU, multi-machine code, especially from scratch. So next I'm going to show you writing multi-GPU code from scratch. It feels difficult, but it turns out it's not so hard. So multi-GPUs scratch. So, so basically you have GPUs, you have PCI switch, you can connect to CPU. This is typical multi-GPU machines. And this tutorial kind of needs more than 1 GPUs. So I run some, there's 4 GPUs here. 4 GPUs on a single machine. Yeah, it's a single machine, yeah. So data parallelism. So basically, for each train batch, I need to, given there's k GPUs, I need to split data into k part. And for each GPU, I compute the gradient with respect to the weight you have using the ith part of data on the ith GPU. Then later on, I need to aggregate all this gradient together. So then, to update the gradients, what I can do that I can copy the aggregate gradient to each GPU and update the weight on each GPU independently. So this is a typical way, the one way to implement data parallelism. I'm going to show you how to implement these algorithms actually here. So one thing here I mentioned before that MXNet can do all this computation in parallel automatically. So I show you here.
When you sum across the GPUs, you do that on the CPU, do you?
I not necessarily do on GPU. On CPU, I can copy to GPU as well. I can sum on GPU. So here, so here I show that I import MXNet NDArray interface. I create a random variable. It's a large matrix. I do matrix multiplication. And the print the time currently I have. Then I copy to as numpy. Basically, I wait until it's ready. So you can see that the result here that when you finish this line's results, you spend nothing here. You just push the operator into backend. The Python thread is blocked until you call as numpy or wait to read or print y. You actually wait until the workloads are finished. So this is actually the time you get all this thing finished. So by these lazy evaluations, so the backend engine, we can get more workload as you can see. So then when you get more workload, you can analyze the dependencies between all this workload and try to run things in parallel. So, so I can show you here. There's a function. Given each x, I run 10 matrix multiplication and return the result. The wait explicitly wait until all this workload are ready. For each result, I call wait to read. So basically, I can run and wait. So I'm going to show you thing here. I first create the data on GPU 0. That's a large matrix. I also copy the result to GPU 1. The first time, what I'm going to do is that I run on GPU 0 and wait until ready. So I run GPU 1, I wait until ready. So I serialize it until that I know that I need to run things sequential. So I can print the time. The second way that I run it, and wait at the end. So in which case, I hope the system will be smart enough to run these two workloads together. So because I wait after all this workload have been pushed into backend. Okay, if I run it, so you can see that run on 2 GPUs and on sequential it takes 2 seconds. And if you run parallel, you should take 1 second. So it shows that it's almost a perfect parallelizations. Because there's no dependency between these two results. So I can issue these two things together and run in parallel. Okay, so is there any questions here? Okay, good. So we can run in computation parallel. We can also run computation and communication parallel. So here I show you that I do another copy. So copy means I copy the data from one device to another device. So I copy all this result here to a target device here. So what I do in here, I run GPU 0 and wait, and then until it's ready, I copy data to GPU to CPU, and until it's ready, wait until it's ready. And so I first run computations and run communications. So the second way I do that, I run it and then copy it and until the result's ready. Hopefully we can do that because we repeat the result by 10 times. So what we can do that when the first matrix is finished, you need to copy directly, not waiting the second one finish. And then you run the second result and copy. So you can kind of parallel all these communications and the computation. So what you can see that the result here, if you run first and copy later, you have the total time is 1.6. And if trying to run parallel, you can reduce a little bit time here. So the time you reduce is actually the communication overhead. Here is still computational dominate, but now because computation is much bigger than communication, so then using this parallel, you can hide all this communication cost. So this is why MXNet can achieve almost a linear speed up using this backend technologies. So just using this interface, so basically you write anything in sequential, and in normal way you don't call wait, and then MXNet is able to parallel all these things for you. So which means that we can actually write a multi-GPU program from scratch easily. You don't need to see any parallelizations here. So similarly, I defined the convolution layer as before from scratch. Define the network, define the parameters, and define the networks is a MNet. So I use the loss function. I have the SGT. So this is exactly the same thing we have been talking about at the convolutional from scratch notebook. So now we need to have more things, how to run things in parallel. So the first one is like, given the parameters, I want to copy that particular into a particular device. So I want to copy the parameters onto a particular GPU. What I do that I create the new parameters, which I copy this. For each parameters here, I copy into a particular GPU, and also attach gradient to that. I return the parameters. So okay, this is copy parameter into a particular GPU function. The second thing is all reduce. So given all these gradients, I want to sum these gradients and broadcast gradients to all the GPUs. So basically what I do that, I add all this data onto data 0. So data contains a list of gradients sit on different GPUs. So what I'm trying to do that, I add all this data from other GPUs to GPU 0. So basically this do, for each I from 1 to length of data, I copy to data 0's context and add into GPU 0. So then I copy the new result to every other GPUs I have. So basically sum all these gradients and then broadcast. So this is the second function we have. Okay. The third one is how to split the data. So given the data, given a list of contact, I can evenly split it. I can return a list. So for each GPU, I can evenly split into on the first dimension, and then copy to the according context. Basically, given data batch, if I have 4 GPUs, I partition into 4 parts, and each part, the ith part goes to the ith GPU. So this is what it does. So within these 3 functions, now we can write the training loop. So it's fairly easy. It's very similar to the previous one we have. So you can see that given the data batch, I first split and load into the context they have. And then I run the forward pass on each GPU. What you can see that so because data and the label contains a list of GPUs, I enumerate all these GPUs, and I call the nonlet given the X, W, and also compare the loss. So basically here, I write a program, looks like I iterate all the GPUs and the sequential and compute the loss and push the loss into something here. When you finished, I can run the backward because I have multi GPUs. For each loss, I need to run the backward. So now when you finished, you can have gradients on each GPUs. Now next time. Yes, if you don't call wait here, everything should be pushed into backend via running parallel. So finally, then you can all reduce the gradient together to broadcast. Then you can run SGD on each GPU independently. So you can see that sequentially run forward on GPU looks like sequentially run backward on each GPU, aggregate the gradients, and sequentially run update the parameter on GPUs. So this is kind of, you don't need to write parallel code. So you can serial code, but if you don't call wait, then everything should push directly into the backend and try to run parallel.
How do you find the synchronization point when all the GPUs are done so that you can do this aggregation?
Yes, I'm going to show you later. I can print the loss.
I just mean you need a callback to when the GPU is done or something, or it's automatic somehow.
People don't need to worry about that. So we use callback to implement it, but people never need to write callback functions. You just print the result. The thread will block until the results are ready.
Okay, so when you call print, that's when you get the blocking. So you
Yeah.
set up all your calculation, you start them, and then you ask for the result, and then you wait.
Yes. Once you want to print, if you don't print, everything can be within MXNet. We don't need to worry about it too much. So similarly, I skip this one. I can do how to validate it similar, but I just on this first GPU you can easily to run some multi GPUs. So okay, so I have everything here. I can write the training loop. Training loop is very similar. For given number of GPUs, I create a context, which is a list of GPUs I have. And then I get mlist, create data iterator, so it's as similar as before. The next thing that, given each parameter, I need to copy into each devices I have. Then I iterate over each data batch. I record the time, I reset the time. Then for each batch on the training data, I train batch all GPUs. Here, particularly, I want to benchmark something. So because I want to benchmark, I call wait to all. Wait all. So wait all this computation are done. But in practice, you don't need to do that. You can always run it until you want to print something. Then you can do validation, something like that. So if you don't want to do that here, sorry, this is for only benchmark. The system will only block here at here. So basically, the valid batch I do as Scala, which means convert from MXNet data into a normal Python float. Because Python doesn't support lazy validations, we block here. So basically, the valid batch at the end, I wait until results are ready. So ideal case, I don't wait until I run train and validation and all this in parallel. But here, I just want to benchmark it. I just call wait to all. So something here, you can run on single GPUs, which batch size 64, and use a particular learning rate. You can see that each time costs about 5.3 seconds, 4.9 seconds. Then, well, you can run on 2 GPUs, and you also increase the batch size, double the batch size, because I want each GPU have the same batch size. And then I also increase the learning rate to get a little bit faster convergence rate. Well, you can see that now the training time reduces to 3.2. So it's not ideally 2 times speed up, but because the workload is pretty tiny, it's a very similar net, also small batch size, but you can still get almost like from 5 seconds to 3 seconds. So even that you can write everything from scratch, the system will automatically parallel that for you. Okay, any questions here?
I was thinking about the weight sharing. I think it was automatic here because it just used the same weight tensors, right?
Yes.
Yeah.
So I copy the weight, actually.
Yeah. And it's, if you want to do things like triplet training and so on, it's a similar concept there, I guess. You just copy it manually.
Yes, you can decide to copy manually, or you can do fancy multi-GPU training. But you can the basic idea that you can hack all this in by hands, but the system will be automatically parallel for you. You don't need to worry about performance.
About visualization, in TensorFlow, you have things like tensor board and so on, where you can visualize things like the statistics of the gradients and the learning curves and so on.
Yeah, we support TensorBoard as well, actually. We support TensorBoard as well. We can dump the result into a portal buffer and visualize on TensorBoard.
Oh, you can use even TensorBoard?
Yes, we can use it. Yeah.
And even if you do Hybridize, you can still get the internals like...
Yes, yes. You basically Hybridize, you can still plug in something there, you can get the result. Yeah. So question?
When you use multiple GPUs and multiple machines, what's the relationship with the hybrid log? Can you use, like that's kind of like internal for each neural network?
So you mean the question that when you use multi-GPUs, how you hybridize the network? Yeah. You can use directly. You don't see any. So the hybridize only changes that if you have fancy things on the forward pass, you can skip the forward pass, but all the other interfaces are same thing. You don't see any performance. So we don't add particular thing into the forward pass. So then hybridize works well here.
If I would like to write my own visualization of weights, for instance, in the imperative mode, I can just pick them during the training class.
Yes.
So printing, I guess, a problem. But if I do hybridize, I only get to press run for this function. Can I get to the cached values that you have on the GPU somehow?
You can. So the question that when you do hybridizing and you want to hack the thing, you can do that. Hybridizing, when you communicate the weight, you don't hack the forward pass. You only hack when you backward is finished. How to get the gradients, how to map that. So hybridize is not related to how to communicate the gradients. Hybridizing only control the forward pass. So yeah. So quickly, I'm going to show you that how to use multi-GPU with Gluon. I mentioned that you only need to, well, Gluon here, I define the network using sequential interface, I create a loss. So the only thing here, so Gluon knows about how to deal with multi-GPUs. The only thing that I want to run GPU 0 and 1, I just initialize, give a list of contacts. It will automatically initialize a parameter and broadcast all the results on multiple GPUs. So this is basically you have nothing to change comparing to the CNN with Gluon notebook. You only need to tell, okay, I'm going to use 2 GPUs. Similarly, Gluon have a split and load functionalities, just as what we mentioned before, how to partition the data and how to load into different GPUs. I'm going to skip this one. So yes, I cannot skip how to initialize all the things. The only thing here comparing to a single GPU that similar to what from scratch, I need to iterate over all these GPUs. Similarly, I iterate the forward, I run the forward, I calculate the loss on each GPUs, and I can compute the loss function. So it's very similar to from scratch. So I can skip these things. So just put all this thing together. Very similarly, we split the data, and we run forward and backward on GPUs. So the trainer, we know that all these parameters sit on different devices. It will automatically aggregate all these parameters for you. So you don't need to worry about that. So it aggregates all gradients and update the weight and the broadcast weight. So nothing you need to do. So comparing to the from scratch, the Gluon interface automatically initializes over multiple devices for you, and the update function, the trainer can deal with multi-GPU gradients. Comparing to the single GPU CNN interface, the only thing you need to change is that when you initialize, you give a list of GPUs, and also you we don't have a nice forward for that. You need to manually partition data and run multiple GPUs. So but I feel like we think about how to have a forward pass that can run, a single core forward that can run all GPUs, but we feel like to let user explicitly know that you are using multi-GPU is not a bad idea. So you need to write a for loop here, but I feel like that should be fine. Okay, so this is how to using the Gluon interface to write multi-GPU code. So I think I have 1 minute left. So I probably now to cover the last one using multi-machines. So it's on the notebook here. So multi-machines, you have nothing to change. The only thing that I give a basic idea that the only thing when you define a trainer, okay, it tells me so basically, okay, I can do that way. Because I didn't tell you what is key value store it is. Basically, you only need to when you define a trainer, it tells me, okay, I'm gonna use the distributed key value store, not the local one. In default, I use the local, but in distributed training, I use a dist key value store. So that's the only difference you have. Then you can launch your multi GPUs, and then you can get the thing work nicely. So this is the only change you want to make. If you're interested, I do have this notebook. It's to explain how actually we map worker server into different machines, and how the underlying implementation, this is a key value store I mentioned on the slides, so basically the local one use the key value store, local key value store, but distributed one you just use distributed key value store. So this for data communications. So I think, yeah, I just want to finish in time. It's 12 o'clock. So thank you guys. So thank you for coming. So it's the last day. Usually people go happy, but thanks for coming. So if I have questions, we can talk offline. So yeah, thank you guys.